If you've ever stared down a complex chemical reaction and, tried to balance it, you know that exact moment. That moment when inspection, which is really just a sophisticated term for educated guessing,
Yeah.
just completely fails.
It fails hard, and that's a big problem.
It really is. We're talking about quantitative chemistry today.
Huh.
And, you might see balancing an equation as just this basic high school algebra problem, but it's so much more. It's the foundational application of the law of conservation of mass. If those coefficients are wrong, everything that falls, from drug manufacturing to material science, it's all fundamentally flawed from the start.
It is the highest stakes setup in chemistry. An unbalanced equation immediately gives you incorrect mole ratios.
And that error doesn't just stay there.
No, it cascades, it torpedoes your stoichiometry, it invalidates your titration results, and it throws off all your thermochemistry. In industry, this is the difference between an efficient, cost-effective process and, well, one that produces just major waste and poor yield.
So our sources today, they show us how to move past this guesswork entirely. We've got material ranging from advanced chemical mathematics, proposing a novel, almost universal method for balancing, all the way to field guides on avoiding the most common, costly calculation pitfalls. So our mission today is to give you the key to solving any balancing problem, no matter how intimidating the molecules look.
It's a powerful tool.
Okay, let's unpack this. Let's start with why the old school methods so often leave us stranded.
Well, the first method everyone learns is balancing by inspection. Making successive educated guesses.
Right.
And it works brilliantly for simple, short equations, but the moment you introduce half a dozen complex reactants and products, or you have to balance mass and electrical charge.
Like an oxidation reduction equation.
Exactly. At that point, inspection just becomes a random, haphazard, and often impossible task.
So if inspection fails, what's the natural next step people try?
Yeah.
And why does that approach still fall short for the really complex reactions?
The next jump is the algebraic approach. You assign variables, x, y, z, to the coefficients, and you set up simultaneous equations based on the atom counts.
Which is a huge step up.
It is a huge step up. It uses the mathematical power of matrix inversion, which is readily available in software scientific calculators. However, this approach is fundamentally limited. It has a critical flaw. It assumes the equation only has a single, unique solution.
Wait. You're saying that the idea we've all been taught, that every skeletal equation has just one perfect answer, isn't always true.
That's exactly what I'm saying. The traditional approach instills this notion of a single right answer. But mathematically, a given combination of reactants and products might yield one of three possibilities. It might have no solution at all. It might have that one unique solution we're always looking for. Or, surprisingly, it may have an infinite number of solutions.
An infinite number.
An infinite number. And if your equation falls into that last category, the standard algebraic matrix inversion just breaks down. It can't handle it.
That is wild. You mean you can write a calculation that tells you the equation isn't even chemically viable as written?
Precisely. Or that there are multiple, completely valid sets of coefficients that all work.
And this is where the matrix null space method enters the chat, right? Because it sounds like it's specifically designed to handle these non-unique scenarios.
Exactly. And here's where it gets really interesting. The matrix null space method is universally applicable because it doesn't look for a single solution. It looks for the conditions where the conservation of mass is met, where the net change in all atomic species equals 0. This is the very definition of the matrix null space, or the kernel.
Okay, so conceptually, what is this null space? If the original matrix represents the composition of the chemicals, what does the null space represent?
Think of it this way. The matrix composition tells you what atoms you have. The null space vector represents the specific quantities of those chemicals that, when you add them all together, sum up to 0 net mass change.
So it's the set of all possible proportions that satisfies the law.
It's the set of all possible relative proportions. Yes.
And the mathematical breakthrough here, according to our sources, is that you don't need some specialized supercomputing software to find this. You can use existing common matrix inversion functions in standard tools.
Yes, that's the innovation. And the power lies in this concept called nullity. The nullity is just the dimensionality of that null space. It tells you how many independent solutions exist. So if the nullity is 0, the required relative quantities just don't exist. No solution.
Okay, and if the nullity is 1?
If the nullity is 1, you have that single unique set of proportions we usually look for.
And if it's 2 or more?
If the nullity is 2 or greater, you have an infinite number of solutions. This is because any linear combination of those 2 or more independent solution vectors will also balance the equation. They represent multiple valid reaction stoichiometries for the same skeletal equation.
Okay, let's take that example you brought up. The reaction involving potassium iodide, potassium chlorate, and hydrochloric acid.
Yes, text QI plus text KCl3 plus text KCl plus text KCl plus text HDL.
Right. Trying to balance that by inspection would be torture.
Oh, it's highly non-trivial. With the null space method, though, you first construct your chemical composition matrix. For this reaction, you have 5 elements, K, I, O, H, and Cl, and 6 chemical species. So that gives you a 5x6 matrix. You then compute its rank, which is the number of independent element conservation equations. The rank here is 5.
And the nullity equals the number of species minus the rank. So 6 minus 5 gives us a nullity of 1.
Right.
So before doing any other calculation, we know for certain there is one and only one unique set of coefficients that works.
Exactly. The software then processes the matrix to extract the null space vector. And this vector, it gives you the relative proportions. They're often in fractions, decimals, and they include negative signs.
The negative signs just mean they're reactants, and the positive are products.
That's all it is.
And step 7, the scaling. That's where we convert those messy ratios into the smallest set of whole numbers, the final coefficients. For that example, the null space vector is eventually scaled to coefficients of -6, -1, -6, 3, 3, 7.
Which yields the beautifully balanced equation. $6 text Ki plus 1 text KClO3 plus 6 text Cl plus 3 text I2 plus 7 text KCl. This systematic process handles equations so complex or almost absurd. Sources mention it successfully balancing what they call the diabolical example, which involves molecules like text Tr7, text Am, and multiple charged ions, all balanced simultaneously.
Wow. You simply cannot guess those coefficients. It's impossible.
You cannot.
The power of that matrix system is the ultimate lesson here. Precision in quantitative chemistry has to start with mathematical rigor. And that rigor is especially critical when you're dealing with reactions that involve electron transfer, redox chemistry. This is a perfect transition, actually, because balancing redox reactions manually requires tracking electrons. That's another whole layer of complexity that the matrix method naturally handles. Redox, short for reduction oxidation, describes any reaction where atoms change their oxidation number.
Okay, let's just nail down the modern definition.
Right.
Oxidation is an increase in the oxidation number. That means a loss of electrons.
Right. The mnemonic OLL, oxidation is loss.
And reduction is a decrease in oxidation number, which means a gain of electrons. RAC. Reduction is gain. And they are inseparable. They always occur together.
Always. And to quantify this change, we use the oxidation number, or ON. It's essentially the hypothetical charge an atom would have if all its bonds were 100% onic. It can be positive, negative, 0, or even fractional.
Fractional, you mean like the iron magnetite, Tex043?
Yes, exactly. There, the iron has an average ON of positive 8/3. It's an average charge, reflecting the sharing across the whole molecule. And we have standard rules to help calculate this. Group Ia is +1, fluorine is -1, oxygen is generally -2. Tracking the change in these numbers is the basis for what's called the law of equivalence.
Okay, the law of equivalence. That sounds like a powerful simplification tool. What does it actually allow us to simplify in, say, a complex titration calculation?
It simplifies the stoichiometry immensely. The law of equivalence states that reactants react and products are produced in equal numbers of equivalents. So it's a perfect 1-to-1 to 1-to-1 ratio, but by equivalent, not by mole. This is a massive shortcut. And to calculate equivalence, you just take the number of moles and multiply by something called the naught factor.
Which brings us back to that naught factor or valency factor. How is that determined in a redox scenario?
For a substance in a redox reaction, the naught factor is simply the net change in oxidation number per molecule. For example, if a molecule contains 2 atoms of X, and each one of those atoms changes its ON by 3, the total net change per molecule is 6. The naught factor is 6. And this number is the mathematical link that allows the law of equivalence to work. It converts our standard moles into these equivalents that always react in a neat 1-to-1 ratio.
Okay, so now that we've established how to precisely balance equations and quantify electron transfer,
Right.
we can move to the final high-stakes application. This is stoichiometry in industrial production. This isn't just theory. This is about maximizing output and minimizing waste.
Absolutely. Stoichiometry is fundamentally about ensuring we have accurate proportions. To maximize profit and minimize waste, you absolutely must identify your limiting region. This is the reactant that is entirely consumed, and because of that, it stops the reaction dead in its tracks.
And it leaves the excess reagent behind. You used a great non-chemical analogy earlier. Let's go back to that car assembly line.
Right. If you're building cars and you need 4 wheels and 1 steering wheel per car, you start with 400 wheels and 125 steering wheels. Now, even though you have way more wheels, the 4-to-1 ratio means those 400 wheels can only make 100 cars. But the 125 steering wheels could have made 125 cars. The wheels are the limiting region. They dictate that you have to stop at 100 cars.
So the lesson there is you can't just look at the initial quantity. You have to look at the quantity relative to the required proportion.
Exactly. And that leads to the best strategy for calculating the limiting region. You take the initial moles of each reactant and divide that number by its stoichiometric coefficient from and this is key, the balanced equation. The reactant that gives you the smallest quantity per coefficient ratio is your limiting region, every time.
And the alternative method is to just calculate the potential output, right? Determine how much product each reactant could theoretically produce. And whichever reactant yields the lower amount of product is the one that limits the total output.
And that lower amount is the critical number we chase in industry, the theoretical yield. That is the absolute maximum possible quantity of product you can make given your starting materials.
Okay, before we wrap this up, we need a final word on avoiding common pitfalls. Because so many calculation disasters aren't caused by a failure to understand the null space method or the null factor, but just by sloppy habits.
That's so often true. The first trap is complacency about the fundamental balance. Even if a question doesn't explicitly ask you to balance the equation, you must always verify the mole ratios are correct. As we've established, if those ratios are off, your limiting region calculation, your yield, your titration results, they're all worthless.
Another insidious trap happens in equilibrium calculations, specifically with Casey the lawyer and Casey stores.
Yes, you have to be rigorous about excluding the concentration of solids and pure liquids from your equilibrium expressions. Their concentrations essentially remain constant, so they get folded into the value of the equilibrium constant itself. Including them fundamentally misrepresents how the system responds to change.
And then there are the vocabulary traps, the subtle differences between commonly confused terms that can lead to major operational errors.
Oh, definitely. Think about the difference between molarity moles per liter of solution and molality moles per kilogram of solvent. They seem similar, but they're completely different units that are critical depending on whether you're working with changing temperatures. And, confusing enthalpy, the energy change with entropy, the measure of disorder, can lead to catastrophic failures in predicting if a reaction will even happen.
And finally, a big picture warning. Never, ever ignore the context.
Right. Reaction conditions, temperature, pressure, the presence of a catalyst, they aren't just throwaway details. If you're dealing with something like the Haber process, for instance, ignoring the pressure and temperature effects means your predictions about yield will be completely, totally wrong. Context dictates the chemistry.
This deep dive really confirmed that precision is the absolute foundation of chemistry. We went from the struggle of simple guesswork to a universally applicable matrix solution, confirming that those precise coefficients are the bedrock of quantitative analysis. If you need to know how much product you're going to get, you first have to master the mathematical input, regardless of how complex that reaction looks.
And tying it all the way back to the mathematical elegance of the nullity concept, if you ever create that chemical composition matrix and find that it's square and mathematically invertible, well, that means the reaction, as you've written it, cannot be balanced under standard conditions. It means the conservation of mass is not being satisfied.
So the next time you encounter a chemical equation that just seems impossible to balance, consider this. Are the fundamental components truly unbalanced? Or is a common overlooked solvent like water in an aqueous environment the invisible reactant required to satisfy that universal law of conservation of mass?